In this video, we're going to be looking at the index laws and looking at how, if you have an expression using these laws, you can simplify it down. So the different laws are basically just referring to different ways to simplify index or expand them out, and they are important as they are different to multiplication and addition of just integers. But firstly, what do I mean by sort of the index laws? Well, here you have a base number, so this is an integer, and then it's to the power of something. So, example, 2 to the power of 3 is equal to 8, and x to the power of 3, so it's a cubic, is equal to x times x times x. So when I'm talking about the index, you could also think about these as like the power laws. So I'm referring to, this number here can be referred to as the index, that's why it's index laws. However, commonly people just refer to it as the power, so like 2 squared, 2 cubed, 3 to the 3 squared, etc. And then simplifying those, we can use these index laws. So firstly we have 2 here, and then these are probably the most common ones that you'll use. So we have a to the x times a to the y is equal to a to the x plus y. So if a to the x times a to the y is not equal to a to the x times y, so you can't just put that multiplication and then turn it up to the top. Rather, as this shows up here, you have to have a to the x times a to the y is equal to a to the x plus y. So when you go from timesing two of these numbers together, and then you changing that into one base with the index, that now becomes a plus. So the times, you can sort of think about it, goes to the plus when you're going from timesing two numbers and you're putting that plus in the indexes or the powers. So then when you divide, there's a similar thing that happens here as well. So you have a to the x divided by a to the y. So instead of a to the x divided by a to the y, that does not equal that. Rather, looking at this formula, we see that a to the x divided by a to the y is equal to a to the x minus y. So you're going from divide to minus. And you can see how that is similar to this one here, where it's times the positive plus or sum, and then from here it's going from divide to minus. So you can see a few examples of this. For example, if we have 2 to the power of 3 times 2 to the power of 3, this is equal to 8 times 8, which is equal to 64. Now we'll test this out. So 2 plus 3 is equal to 2 to the 6, which is equal to 64. But if you put 2 to the 3 times 3, this will give you 2 to the 9. So you think when you're timesing these together, and we're expanding this out, so we're here, you effectively, when you're going 2 to the 3 times 2 to the 3, this is equal to 2 times 2 times 2 times 2 times 2 times 2. So you can see that the amount of 2's is going to be equal to 6 rather than to 9. And that's why you have to add them together rather than multiply these two indexes. Similar thing happens when you have these divide. If you have 2 cubed divided by 2 squared, this is equal to 8 divided by 4, which is just equal to 2. So this is, as you can see, this 2, that's equal to 2, 3 minus 2, which is equal to 1, so 2 to the 1 is just equal to 2. So this formula holds. And if you expand this out, you have 2 times 2 times 2 over 2 times 2. And you cancel each one. So 1, 2 cancels with another 2. So it makes sense, that's why it's minus, because for each 2 up here, you're going to minus, and then whatever the leftover is, that's going to be however many power it's going to be. So that's 1, but if it was, let's say, 2 to the 4, 2 to the 4 divided by 2 to the 2, then we'll just be left with 2 to the 2. Another rule is that a to the x to the power of y is equal to a to the x times y. So this one is different. It's not timesing by y, but rather we have a to the x, and then once again we're putting it to the power of something else. So it's basically putting to the power of a twice. And then this is going to be equal to a to the x times y. So before we had times going to positive, divide by going to negative. So we can see that we're sort of like going down one power, and you can see how this happens. So when you're going from the power, we now change this to multiply. So when you have like a to the x to the y, this now becomes x times y. You can see that like 2 to the 3 to the power of 2. And the reason why it's multiplying is because this will give us 2 to the 6. That's because you have 2 to the 3 times 2 to the 3. So instead of having 2 to the 3 something else, you have 2 to the 3, you're timesing it by itself. So you're going to get 6 different, like 2 by 2 by 2, 6 times. And you can get that number by having however many powers are in each individual one, and then timesing it by however many times the number is repeated. So these two laws are especially important when we want to look at what the graph of an index looks like. So let's say the graph of 2 to the x. So the first law is a to the negative x is equal to 1 over a to the x, assuming that a isn't 0, and then a to the 0 is equal to 1. So for that, it's like 2 to the 0 is equal to 1, 100 to the 0 is equal to 1, negative 50 0 is equal to the 1. So they're all equal to 1 apart from a is equal to 0, so we don't worry about that case. Now if we're graphing, let's say 2 to the x, we can see that the graph is going intercepts at 0, 1, and that's because of this rule here. Then it's going to increase, as we would expect. But what happens on this side? Well, it gets smaller and smaller and smaller, but it never becomes negative and approaches here. And we can think about that as an asymptote. So here is y is equal to 0. Now, the reason why it never becomes negative is due to this. Even when x is negative, so x is a negative number here, such as there, this causes it to have 1 over a to the x. So it's still going to be positive, but as a to the x goes to infinity, 1 over a to the x approaches 0. So the following laws are more about notation wise. So you do need to know them. However, they're more about notation. So you're not going to use them to sort of simplify as such, but rather you just need to know them. So a to the 1 to the x can be written as x like this. A to the x over y can be written such as that. And then these 4. So make sure you're familiar with all of them and be able to recognize them and be able to implement them. Probably the most important one from these 4 is this one here. You have cumulative, where you have a to the bx, which is equal to a to the x times b to the x. So now we're going to look at an example about how we can use the laws we just learnt and simplify this expression here. So we have 3 to the n times n to the n plus 1 times 12n minus 1, 9 to the 2n times 12n. Now lots of way to go about this, but I can sort of see here that there's 9 and 3's, and well, 9 I know is equal to 3 squared. So if I can get stuff in terms of 3's, then I'll be able to cancel out. Now 12 I know is equal, well, there's 12 and 12, so I'm guessing we may be able to cancel something out there. So the first thing is I'll convert the 9's to 2's, and then I'll see if I can cancel the 12's. So start off with 3 to the n times 3 squared n plus 1 times 12n times 12 minus 1. Now, I could split this up by using the law that when you have like 12 to the a times 12 to the b, this is equal to 12a plus b. So that's effectively what I've done here. I had 12 to the a plus b, so I split that up into 12a times 12b, where b is negative 1 and a is equal to n. So I've got that. Now 3 squared, I just showed how that happened. And now the bottom. The bottom comes 3 squared 2n times 12n. So firstly, I can cancel these 12n's. So that's down. Now next, I can expand these out. I can go 3n times 3 2n plus 2. And remember, something to the power and then to the power again, you can times these two numbers. That's what I've done here. Divide, and then I'll times these numbers like I did above. So I get 3 4n. Now, 3 to the 4n is equal to 3 to the 2n times 3 to the n times 3 to the n. And that's because 2n plus n is equal to 4n. Now, if you don't, you can probably just split up to 3 to the 2n and then 3 to the 2n, but I'm just going to skip a step. However, the main thing to realize here is you have 4n and you have a 2n. So we want to get rid of that 2n, so we can split that 4n into that 2n and another 2n, but I split into 2n, n, and n. And all those numbers added up together will give you 4n. So this will give us 3 to the n times 3 to the 2n times 3 squared. And you can see how I've done a similar thing as I did up there when I split this up. That is divided by 3 to the 2n times 3 to the n times 3 to the n. So I forgot the 12 to the negative 1, so that's there. I can bring that down to the bottom, because remember 12 to the negative 1 is equal to 1 over 12. So that's 12 there. Give myself some more room. And then the 3 to the 2n cancels with that. 1 of the 3n's cancel with that. And I get 9 over 12, which is 3 on 4, over 3n. So this is equal to 9 on 12 over 3n. These cancel, give us 3 on 4. So we have 3 on 4, 3 to the negative n. You can remember negative n is just 1 on 3n. So this expression here can be simplified down. And that's the main reason why I use index laws for simplification, which mean that if you wanted to graph this, it may look very hard. However, once you simplify it down to something like this, then it's in a form in which we can graph.